So I am happy to introduce Dr. Pratyusha, again our former student, who is now in BITS Pilani, Hyderabad campus. She will be speaking on elementary linear groups, Suslin's normality theorem and beyond.
Thank you, Srinivas, for the introduction, and I thank all the organizers for the invitation. And I'm really happy to be here at this occasion when the institute is celebrating the 60th birthday. Uh, so I was told to give a talk which should be accessible to everyone, and I thought of talking about normal subgroup. So everybody understands the groups and normal subgroups. So in the study of groups, identifying the normal subgroups are quite important, because every time we can identify a normal subgroup, we can actually construct a new group, namely the quotient group. So as the title suggests, I will be talking about I will begin with the elementary linear group and Suslin's normality theorem for the elementary linear group. But many people have identified that this the analogous theorem, analog of Suslin's normality theorem can be proved for many other groups as well. So as I go on, I will recall the definitions and state the theorem in those setups. So, okay. So throughout my talk, I will assume that R is a commutative ring with unit element, and I will be an ideal of the ring. And small Eija, I'm just trying to save myself from this light, but it's somehow hurting my eyes. Yeah, maybe it's a good spot. Yeah. So small Eija, that denotes an n cross n matrix, which has A at the ijth position and zeros elsewhere. Here, small a is an element from the ring R. And then we look at this elementary linear matrix, which I denote by capital Eija, which it is the identity matrix of size n plus small Eija. Here we have the restriction on I and j. They are two distinct integers between 1 and n. So one can see that these matrices are of determinant 1. So you can look at the subgroup of SLNR generated by the elementary linear matrices, which is called the elementary linear group and denoted by capital E suffix NR. Then one can also talk about the true relative elementary linear group, which is denoted by ENI for an ideal I. This is generated by Eijx, where x is coming from the ideal I. And then next we look at the relative group ENR comma I. This is basically the normal closure of ENI inside ENR. So what do I mean by that? It's a group generated by the elements of the form G8G inverse, where G is an element of ENR and H is an element of ENI. So the result Suslin proved is as follows, that the relative elementary linear group EN R comma I, this is a normal subgroup of GL and R for size bigger, when the matrices are of size bigger than equal to 3. So the size bigger than equal to 3 is important here, because there is an example by Kohn where he considered a ring, the ring was a polynomial ring in 2 variable, where he showed that in size 2 this result is not true. And this result was quite remarkable, but anybody would be able to read the proof in the sense it only involves some clever matrix computation, nothing more than that. And one of the nice application of this result that was also proved by Suslin, that over the polynomial ring over a field, the SLN and EN, if we pick up any element of SLN over the polynomial ring over field, that can be written as finite product of elementary matrices over the polynomial ring, again for size bigger than equal to 2. So this is the normality theorem of Suslin, and now I will go on talking about similar theorems in other setups. So whatever definitions are required, I will recall that. So now I come to the definition of elementary symplectic group. So how do we define that? We first considered this psi 1, which is 0, 1, minus 1, 0, the 2 by 2 matrix. Then one can talk about the standard alternating matrix of size 2n, which we denote by psi n. Psi n is of size 2n by 2n. So it has these blocks 0, 1, minus 1, 0 along the diagonal. And then we look at the symplectic group. I mean, I am denoting that group by sp2nr. These are all the invertible matrices of size 2n, which will satisfy this equation alpha transpose psi n alpha is equal to alpha. So this is the symplectic group. Next I want to talk about the elementary symplectic group. So to talk about the elementary symplectic group, I first bring into the picture a permutation sigma of natural numbers 1 to n, and so sigma is defined as sigma 2i goes to 2i minus 1 and sigma 2i minus 1 goes to 2i. Then we look at these matrices Seija. So for that, I mean, we pick up two integers between 1 and 2n, distinct integers, and for an element A in the ring, we define Seija as follows. When I is equal to sigma j, then it's just identity matrix plus small eija. When I is not equal to sigma j, it has another description. And one could check that all these Seija, these matrices will actually satisfy this equation alpha transpose psi n alpha equal to psi n. So these matrices belong to the symplectic group. So these are called elementary symplectic matrices, and the subgroup generated by them is called the elementary symplectic group generated by these elements. In this setup also, one can talk about the elementary symplectic group over the ideal generated by Seijx, where x is in the ideal, and then one can take the normal closure. So in this case, V.I. Kopeiko, he is a student of Suslin, he proved that ESP2n r comma I, the normal subgroup is, the relative group is a normal subgroup of the symplectic group when size is bigger than equal to 4. And using this, he proved a similar result, that any symplectic matrix over the polynomial ring over a field is actually finite product of elementary symplectic matrices over the polynomial ring. And next we will see the similar kind of result for the orthogonal group. So for the orthogonal group, I start with the standard symmetric matrix of size 2n. So for that, we consider psi 1 tilde to be 0, 1, 1, 0, and look at the 2 by 2 matrix which has these 2 by 2 matrices along the diagonal. And then orthogonal group, which is denoted by O2 and R, is a group generated by all those invertible matrices of size 2n, which will satisfy this equation. Although the equation looks quite similar to the previous one, but the generators are quite different. So here the generators are OEIJA, we are denoting by. So here I is always different from J and A is an element of the ring. So OEIJ is the matrix, it's identity matrix of size 2n plus EIJA plus E sigma j sigma I minus A. And again one could check that the OEIJA, these matrices belong to the orthogonal group. They are called the elementary orthogonal matrices, and one can look at the subgroup generated by them, which is denoted by EO2 and R. This is the elementary orthogonal group. Again, in this case also one can consider the relative group with respect to the ideal and form the normal closure. And this is the result proved by Suslin and Kopeiko, that the relative elementary orthogonal group is a normal subgroup of the orthogonal group for size bigger than equal to 6. And one of the interesting application of this result can be seen here. This was also proved by Kopeiko and Suslin. This says that if F is algebraically closed field of characteristic different from 2, then any quadratic R space, so R is a polynomial ring over a field, this is extended from the quadratic F space. So this result, this theorem is also, before it was proved, it was also known as Parimala's conjecture, in the sense Parimala showed that this result is not true when you are considering a polynomial ring in 2 variable over the reals. So, and she conjectured this result to be true, which was later on proved by Suslin and Kopeiko. All right, this is the, Suslin's results and analogous result in the setup of symplectic group and orthogonal group. Next, I will talk about the transvection groups. It might sound I am suddenly deviating from the elementary setup, but not really. So, transvection groups were introduced by Hyman Bass in the study of projective modules. So, these groups are actually quite important subgroups of the group of automorphisms of projective module. He introduced to address some of the cancellation problems involving projective modules. But the interesting thing is for free modules, this transvection groups actually coincides with the elementary group. So, for the transvection groups, we have the notion of elementary transvection group, symplectic transvection group and orthogonal transvection group. But one can see if we begin with, instead of projective module, if we begin with free modules and we try to look at the transvection groups in case of free modules, it coincides with the elementary linear group, elementary symplectic group and elementary orthogonal group. So, due to that reason, one can think of these transvection groups as the generalization of the elementary groups in the setup of projective module. So, now the question is, the results which we are having for elementary group, can we extend those for the transvection groups? And if we consider the Suslin's normality theorem, here Rabea Basu, A. Bach, Anthony Bach and Ravi Rao showed that Suslin's normality theorem is actually true for transvection groups also, and it's a nice coincidence that Rabea is present here among the audience. So, next I will move to another normality theorem. So, I talked about the elementary symplectic group. So, elementary symplectic group is basically the group of isotropies of the standard symplectic form. So, standard symplectic form was like the 2n by 2n matrix, which has this 0, 1, minus 1, 0 along the diagonal. So, instead of having that standard symplectic form, if I work with any invertible skew symmetric matrix, still we can define another symplectic group. This was introduced by Wasserstein. So, he introduced it for a different purpose. He did not really work with that group a lot, but one could see, like here I am taking phi to be an invertible skew symmetric matrix of size 2n, then one can define this group SP phi r. So, earlier it was SP 2nr with respect to the standard symplectic form. Here I am defining a new group which I am denoting by SP phi r. It is with respect to any invertible skew symmetric matrix. Then, so if phi is skew symmetric, phi and phi inverse can be written in this form, where C and D are column vectors of length 2n minus 1, the entries are coming from the ring. Then one can, given any vector which is of, I am considering them as column vectors of size 2n minus 1, one can construct this alpha and beta which depends on V and phi inverse. And one could check, then okay, so then one could again, using this alpha and beta, construct these new matrices which I am denoting by C phi V and R phi V. One could check that C phi V and R phi B belongs to SP phi R, the symplectic group with respect to any alternating form. It will satisfy the equation. So, one can look at the subgroup generated by C phi V and R phi V, this subgroup of SP phi R, which is denoted by ESP phi R. So, here also one can talk about ESP phi I, where the vectors are chosen from, vectors are of length 2n minus 1, where each of the entries are coming from the ideal. And one can look at the normal closure, which is called the relative elementary symplectic group ESP phi R comma I. So, another interesting thing to note that if we begin with this definition ESP phi R and then we replace the phi by the standard skew symmetric matrix, we get back the ESP2nr, the earlier which we talked about, the elementary symplectic group. So, if due to this reason one can think of this ESP phi R as the extension of the previous definition of the elementary symplectic group. So now the question arises, there we had a version of Suslin's normality theorem. So can we have Suslin's normality theorem for this group as well? And this is a recent result with my student Amruta. We showed that if 2 is invertible in the ring and phi is a skew symmetric matrix of Pfaffian 1 of size bigger than equal to 2, then we do have Suslin's normality theorem for ESP phi R, relative ESP phi group. All right, now next I will move to another result which is named as true relative version of Suslin's normality theorem. This was proved by Bogdan-Nika. This says the relative elementary linear group ENI that is normal in this particular group where it's a subgroup of SLNR generated by all those matrices which are diagonal modulo the ideal. So this is this was Nika's terminology, which is called true relative version of Suslin's normality theorem. So if you look at the proof of this theorem, one of the results which he used heavily to prove this result is this particular result of Tits, which says the relative elementary linear group with respect to the square of an ideal is a subgroup of the true relative elementary linear group when n is bigger than equal to 3. Now, when I was reading this result, although I am interested in the normality theorem, this result of Tits I found it was also interesting to study whether it can be extended for other groups as well. So one of the important application of this result is like there was 2 results of Menike. One was proved in 1965, which was proving that over the ring of integers, if one looks at the principal congruent subgroup, that is equal to the relative elementary linear group basically. That was proved in 1965, and much later in 2000 he proved another result which he termed, he showed that the ENI, the true relative elementary linear group is equal to all those, equal to a subgroup of SLNR generated by all those G such that G mod I is diagonal. Not only that, all the diagonal entries are of the form 1 plus x, where x is in the ideal square. And he termed that result as a counterpart of the previous result which he proved in 1965. But then in this paper of Nika, he showed that these 2 results are not actually different, they are equivalent, and that equivalence was established by using Tits result. So due to that, I was interested to study Tits's result, and what I observed that Tits actually already proved this result for Chevalier groups. So that way this result is already known for all the elementary linear group. So the question is whether it's known for the transvection groups also. So that was one of the recent results where I have shown that Tits's result is true for transvection groups also. So here is my presentation regarding Suslin's normality theorem and true version of Suslin's normality theorem. So I will just quickly go through the reference which I used. This is the result regarding the symplectic group which is currently in archive. Then this is where you can see the Suslin's normality theorem for the transvection group. This is the Bass's book where you can find the transvection groups and so on. This is the Tits's result for the transvection group, and this is Kopayko's result regarding Suslin's normality theorem for the symplectic group. This is Nika's result, and all the details I talked about can be found here. Then this is the main reference where this presentation I have started with, and this is Suslin Kopayko's reference, and finally the Tits's result. Okay, thank you.